Okay, so today we're talking about Chapter 7, Section 4, the graphs of quadratic functions. Now, this particular lecture is going to look, it's going to be a little bit different than what I normally do, mainly because I kind of want things to look nice and neat, and what I'm going to do instead is I'm going to be doing a lot of snipping today. There's not, in fact, there's not any computation, I don't think. It's just really seeing the equation and then determining from that from just looking at the equation or looking at the function, what we're going to be doing. Okay, so let's go ahead and get started here. And again, we're going to we're going to snip this and put it on the front page. All right, and these are just for your notes, right? But I won't be covering it. Instead, we're going to jump straight to example one. And like I said, there's going to be a lot of snipping, and hopefully it doesn't come off as lazy because up to this point I've been doing a lot of computation for you guys. It's just like I said, I want things to look nice and neat. So hopefully it's well received. We'll see. Alrighty, so looking at example one, it reads graph the functions f, g, and h on the same coordinate system. So all we're going to do here when we graph them, okay, is we're just taking the function, right? F of x is x squared, g of x is x squared plus 1, and h of x is x squared minus 2. We're just going to pick some arbitrary numbers, all right? We're going from -3 to +3, and we plug those x's in and we get the y's out. And by doing that, we can see that we indeed plot this graph over here. Right? Now the purpose of this particular exercise is to notice that, well, if we can drag it right, is to notice that they're all kind of the same, aren't they? They are the same. And let's see, while we're looking at that, all right, so the pink is x squared plus 1. Notice where the y-axis, or notice where the y-intercept is. It's right here at 1 on the y-axis. F of x is equal to x squared. That's just a black line, we're going down here. But then we have x squared minus 2, right? It's minus 2 here. And notice how the intercept is down here on the y-axis at -2. Okay, so we're gonna be using that thought process as we move forward here in a moment. All right, and kind of in the same vein, let's look at this one. Current page. Okay, so let's look at this one now. All right, so we have uh, it wants us to sketch these functions. So we have x squared minus 4, x squared plus 7 halves. So if we were to sketch these graphs, all right, so look at A, it's x squared plus 4, I'm sorry, minus 4. Notice how we indeed go down to minus 4. Easy, okay. Well, then we have x squared plus 7 halves, and we notice how we go up to, it looks like 3.5, which is exactly what 7 halves is, right? 7 halves is 3.5. And notice how we have the y-intercept up here at 3.5. Okay, and it looks like the hardest part about this these two exercises, honestly, is to remember that the x squared is basically just a parabola like this. Okay, and then, well, let's try another example, and this is kind of like example one, except for we're not adding or subtracting to the x squared. Instead, we're adding subtracting just to the x. Okay, we're going to see exactly what the whole point of this is here in a moment. Okay. So anyways, again, in example one and two, let's go ahead and look at the difference here. All right, so example one and two, notice how we are, and for this we're not adding or subtracting anything, but notice how we're adding 1 and we're subtracting 2. And we're doing that from x squared. Right here we are subtracting 4 and adding 7 halves. And again, this is from x squared. Well, example 3, notice how we are adding or subtracting from just the x. Okay, well, now let's see if we can't figure out a pattern here. Okay, so and of course, we have our x squared. That's the black one. That's nothing new. That's the same one that was asked to be sketched earlier. All right. Well, what about x plus 1 quantity squared? Well, again, we're in this particular case, our tables are going from -4 to 5. We are adding 1 to the variable. Okay, and so that would correspond with the pink. And notice how it's actually shifted to the left 1 unit. Right? So notice how the bottom of the parabola is no longer at the origin. It got shifted left 1 unit. Okay. Well, look at the blue one. It's x minus 2 quantity squared. Well, notice how we're shifting to the right 2 units. Okay, so a pattern is starting to develop here. And um, do we skip a, yes we did, after example 1. Okay, so let's go back and let's actually put the concepts before the examples. Okay, we're going to do them before the examples just so we can really see what we're trying to do here. So example 1, example 2, example 3. So we're going to put an inserted page here. And we're going to again see exactly what the concept is. All right, so let's go all the way back to before example 1. All right, this first concept we're calling a vertical shift. Okay, so a function of the type f of x is equal to x squared plus k, some k, represents a vertical shift of the graph of x squared. All right, so if our number is greater than 1, we shift up k units. If our number is less than, I'm sorry, did I say 1? If it's greater than 0, we shift up k units. If it's less than 0, we shift down k units. Okay, so looking at this, again, go back to example 1. See, it's a plus 1, so we shifted up 1 unit, the pink line. It's minus 2, so we shifted down 2 units. Looking here, we have a minus 4, so we shift down 4 units. We have a plus 7 halves. Again, that's 3.5, so we shift up 3.5. Right, now let's look at that. That's the vertical shift. Now let's look at the horizontal shift. So the horizontal shift, okay, it's in the form x minus h quantity squared. So a function of the type f of x is equal to x minus h quantity squared, it represents a horizontal shift, right? Well, how far exactly are we shifting? Well, we're shifting h units, right? So if our h, if we have an x minus h, then we're going to be shifting to the right. Okay, now that might seem a little counterintuitive just for a moment, but let's actually show you why. Okay, well, all right, let's bring up the next. So we had x plus 1. So I'm going to use the x plus 1 as an example. X plus 1 quantity squared. Okay. So if we have x plus 1 quantity squared and we equate it to 0, we have x plus 1 is equal to 0, or in other words, x is equal to -1. All right, and notice that is essentially the opposite. I mean, it is in all forms of plus 1. And that's always shift the opposite way. So if our h is greater than 0, then we shift to the, what? I'm sorry. Let's look at this. If we have a negative h, we shift right. If we have a positive h, you gotta be kidding me. This is another, oh gosh, it's another typo in the text. That's incredible. It's the second one that we found, at least in terms of that. Okay, so let's, never mind, minus 1. Never mind. Actually, all we have to do is just put a plus here. So let's mark that out and say x plus h quantity squared. Okay. So let's fix that h a little bit. Doesn't really look that good, does it? X plus h. There we go. All right. And I guess that's really the only typo there. So if we have a minus h, we shift right. If we have a plus h, we shift left. It's just the exact opposite. Okay. And of course, we see this here in this example. We have a plus 1, so we shifted left, the pink one. We have a minus 2, the blue one, so we shifted right 2 units. All right. And again, we're just gonna do some snipping here. I'm gonna pull. Okay, so we don't have a figure F10, so, or 710. So we're going to, for just the purpose of this, we're just going to focus on A. Okay. And again, it's nothing tremendously difficult. We have a -7, so we just since it's a negative sign, we shift the graph to the right. So we start here at the origin and shift to the right 7 units, and we have the blue line. And you know what, let's just go ahead and we can go ahead and put the B on this graph. So let's go ahead and do that. I mean, it's not going to be pretty, but it'll be there. So it's an x plus 1.6, so 1.6, so it's a plus 1.6, so I go to the left 1.6 units, so about right there-ish. And then we just draw the parabola like that. Yeah, that's actually pretty steep. That's pretty wide. I don't know. There we go. Now you know why I wanted to just snip. But this is B. I think there was 8 exercises here. Yeah, it's 8 of them. Okay. So next up, we're gonna be talking about well, we don't have an actual name for it yet in this course. Okay, so we'll keep it as no name. But in I can't remember if it's this class or a later class, we actually call it stretching. And you know what? Now that I remember, let's do this the same way we did the previous ones. And instead of drawing the diagram, let's go ahead and there we go. Let's go ahead and give the concept first. So let's go back. We're going to insert a page. So we're going to give the concept of a stretch and a shrink. Darn it. Okay, well we'll just have to delete that for the later on. So let's go ahead and go over the concept real fast before we actually get to the example. So the graph of a times some x squared, right? So far we've had the x squared plus or minus some number. We've had x plus or minus some number quantity squared. Now we're going to be multiplying it by some number. Okay. Well, if that number is greater than 0, then what we're going to have is a vertical okay. Okay, so that's nice. So we're going to have a vertical stretch. Okay, so this textbook goes about this pretty weird. Okay, so how can I do this? All right. So the way this textbook is breaking it up, okay. Normally we don't even talk about this, but since it's here, we will. But the reason why is because realistically, if we have the a in front of the x squared, okay, we have f of x is equal to some a raised to the x squared power. If this a is positive, then we have a parabola that opens up. If it is negative, then we have a parabola that opens down. All right, and that's realistically the only point of 2 here, okay? Because if we just focus in on what that number is, exactly what that number is, we don't care about the sign. We just care about what the number is. Okay. Yes, the sign does matter because it tells us if we're opening up or down. But like I said, you know what? I will just do this. Let's just forget this. Okay. Obviously, if you're following along with the lecture, you'll know why I'm marking this out. Hopefully, you were actually watching the lecture. But the whole point of a parabola opening up and a parabola opening down, it's just determined by is this a, is it positive? Then we open up. Is it negative? Then we open down. That's it. Now, if we get to the actual stretching and shrinking, this is also pretty easy, but it's also um, let's see, I wouldn't say open for interpretation, but the the magnitude of your stretching and shrinking will obviously vary. Okay, so um, before I get ahead of myself here, let's just go over this example or this definition finally. All right, if our a is some fraction or some decimal, then we have a vertical shrink. If our a is greater than 1, then we have a vertical stretch. Okay, so let's examine what a shrink and stretch means. Okay, so example 5. Let's go ahead and make this large again to really show you. So example 5, we have f of x equal to x squared. Okay, and again, we've seen that before. That's the black line. There's nothing new about it. Okay. Um, I'm sorry. It's the pink line. Okay, it's the pink line this time. Okay. Yeah, it was a little confusing. But okay, so the x squared is the pink line. So on the previous page, we said that if our a is greater than 1, then we stretch. Okay. Well, 2x squared, this 2 is greater than 1. So what we're going to do is we're going to take this pink line, okay, and we're going to we're going to stretch it vertically. So, right, so we're going to have, here's the pink line, we're going to stretch it vertically. And so what we're doing is we're kind of pulling on the strings, and it's going to look something like this. And of course we see that with the black line there. That's what a vertical stretch is. We stretch it. Okay, and again, it's kind of hard to graph it, but I mean obviously on your homework and stuff you'll have your graph and utilities, but you just basically stretch the graph. Okay. Well, a vertical shrink is exactly what it sounds like, right? So this number, 1/2, well, 1/2 is, again, 0.5, which is between 0 and 1. So we shrink it. So for the black line, going from the pink line to the black line, again, pink line to the black line, we take the graph, we take the pink graph, and let's just make this white. And we stretch it vertically. We stretch it, kind of pull it up vertically. Well, that blue line, okay, is a vertical shrink. So what you're going to do is you're going to basically take it the other way and flatten it. So you're going to kind of flatten the line, and that's how we get that graph. And unbelievable. This is, man, there's just typo after typo here. So this h of x is 1/2 x squared. It's 1/2 x squared here, but for some reason it's graphed as 1/3 x squared. Unless I'm missing something. No, it's just another typo. Wow. Okay. I really should have kept track of all these. I didn't realize that there were going to be this many in this textbook. Next semester I'll keep track of them. Okay. And well, I won't say lastly, but we are now given a good way to figure things out depending on what our function looks like. So if we have a function that looks like f of x equal to a times x minus h quantity squared plus k. Okay, the vertex is going to be the very top and the very bottom of the parabola. So notice here this is the very bottom, this is the very top. The vertex is hk. Notice how it is the opposite sign of the h and it's the exact sign of the k. Okay, so remember that. The axis of symmetry, well, it's just going to be h. So we're going to be using that number, the opposite of h. If a is greater than 0, and again, this is what I was talking about before, if it's greater than 0, we're going to be opening upward. If it's less than 0, we open downward. And of course, if we're opening upward, we have a minimum value, and if we're opening downward, we have a maximum value. Okay, so let's put all those into practice and look at this. Okay, so this is, we have everything we need to work on this, and just for the sake of this, let's actually follow along with this for this problem anyways. Okay. So it reads, for A, we need to identify the vertex. Well, again, the vertex, like we said, was the opposite sign of the number inside, right? So this is x minus 3, so it's going to be a positive 3, and it's going to be whatever this is, and that's 4. So it's going to be positive 3, positive 4. All right, sketch the function. We're going to skip that for right now. C, identify the axis of symmetry. Well, the axis of symmetry, as we mentioned, is just going to be x is equal to h, in this particular case is going to be 3. So x is equal to 3. And again, I'm just looking at that. A, B, C, D, we're going to need to identify the maximum or minimum values of the function. Well, uh, looking at the a value, which is 2, okay, since it's a 2, a positive 2, I know we're opening upward. Okay, so that means that this is going to have a minimum at this parabola, it's the smallest part. So we're going to have a minimum value at 3, 4. Okay, and then E, it says use the graph to determine the domain and range. Let's go ahead and snip the graph. There we go. Snip the graph and stick that right here into B. Let's put an arrow pointing to it. Boom. Okay. So indeed, we do see that the vertex is indeed positive 3, positive 4, and it is also, again, a minimum. We see that here. You see the axis of symmetry being located at x equals 3. E wants us to use the graph to determine the domain and range of f. So in interval notation, so the domain, all right, it is a quadratic function, so it is always, all right, and I mean always, going to be negative infinity to positive infinity. Always. The range, okay, so the range is going to be a little different. We're just going to look at the graph, and the range, it looks like it's going from right here at 4, again on the y-axis, all the way up to infinity. Right? So it looks like my range is going to be 4 to infinity. And of course, since we're including the number 4, we're going to put a bracket. So 4 to infinity. Well, there we go. And I mean that was pretty darn simple, right? I mean well, I don't really call it anything. The sandy area here pretty much tells us everything we need to know about our quadratic equation there. And then lastly, kind of the same kind of problem, but now we have um, fractions. Always have fractions, don't we? Okay. So let's go ahead and do this. So we're not gonna follow along with the sandy area. This I don't know. I think we should actually. All right, at least no. Let's not. Let's not. All right, they're giving 200 notes. All right, so we want to identify the vertex here. So the vertex, again, we're going to look at the h value and k value. So the h is a positive 2 inside there, and then we have a negative 7/4. So my vertex is going to be the opposite of that positive 2, so it's going to be a negative 2. And then we're going to take the sign of that negative 7/4, like so. Sketch the function. Again, I'm going to just leave that blank for right now. Identify the axis of symmetry, which is going to be this. So we're going to have x is equal to negative 2. D, identify the maximum or minimum values. Okay, so looking at this particular equation, right, we have a negative out front, right? So the negative right here is out front. So we know since it's negative, we're going to have a parabola opening downward. So what that tells us is that we're going to have a maximum value, okay? Since we have a negative out front, so this tells me that this particular parabola is going to have a maximum value at the vertex, which is going to be at negative 2 and negative 7/4. Okay. And then E, use the graph to determine the domain and range. So again, let's go ahead and look at the graph. Yeah, so we could have pretty easily made this graph, but I like to make it nice and neat. We do indeed see we have the vertex here at -2 and -7/4, and we do indeed see that we are pointing downward. Okay, well, the domain, like I said, the domain of our quadratic equations are always going to be -infinity to +infinity. All right, pretty easy. There's no tricks. That's it. Now the range is going to be just a little different. Okay, looking at the range, it looks like I say looks like. Let me go back. Go back. Okay. We're going from -7/4 down to infinity, right? Because again, all we have to do is just basically look at the vertex, right? We're going from -7/4, and we include it, so -7/4 all the way down to a -infinity, right? And that is the range. And those two problems, I mean, normally I feel like the end problems are usually the harder, more tedious ones, right? In this particular case, all we have to do is just follow along with the sandy area, and of course, the more you do it, the more you'll be like, I don't really need this because I know this information, and then you can solve the problem from there. And yes, that does conclude today's lecture.